Assalamualaikum and hi everyone. Today we are going to continue with our chapter 2, Homogeneous Semiconductor, focusing on Extrinsic Semiconductor. We have covered previously on Intrinsic Semiconductor. Intrinsic Semiconductor is a pure semiconductor that has no impurities. When one electron jumps from valence band to conduction band, one hole is created in the valence band. In the intrinsic semiconductor, the number of electrons or electrons concentration is equal to the number of holes or holes concentration. I hope you still remember this equation, and note P naught equals to Ni squared. Although intrinsic semiconductor may have electrons at the conduction band, but the concentration is not enough to conduct current. Thus, we need extrinsic semiconductor. In this video, we will learn on the characteristics of an extrinsic semiconductor. Extrinsic semiconductor is a semiconductor that has impurities intentionally added to it to increase the number of carriers or carrier concentration to improve its conductivity. The process to add impurities to the semiconductor is called doping process, and the materials used in doping process is called dopants. Dopants to increase electron concentration are called donors. Dopants to increase hole concentration are called acceptors. For group 4 semiconductor material, donors will come from group 5 and acceptors from group 3. Let's see how the N-type semiconductor is created. We know that silicon has a valence of 4 electrons. When an atom with 5 electrons in the outer shell, for example phosphorus, from group 5 substitutes the silicon atom, the extra electron is not needed for the covalent bonding, since there are enough electrons to fill the bonds. The extra electrons can be donated easily to the conduction band. That is why the atom from group 5 is called donor atom. The donor atom is positively ionized since it has lost 1 electron. One phosphorus atom will create 1 extra electron in the silicon without creating extra holes in the silicon. Let's take a look at the band diagram of an N-type semiconductor. Donor such as phosphorus has a slightly different set of energy levels than the silicon atom, and some of these are in the silicon's forbidden gap. This creates the donor level or ED in the band gap. The donor state of energy, ED, is close to the conduction band edge. Thus, it takes only a very small energy by the electrons in the ED to move to EC. When the electron in ED moves to EC, conduction electron is created, but no holes are created in the valence band. So, N naught is larger than P naught. Donor atom becomes positive ions because it donates an electron, and the majority carrier in this type of semiconductor is electron in the conduction band. The electrons donated by the donors are also influenced by the temperature. At T equal to 0 Kelvin, ED is filled with electrons from the donor. When the temperature increases, electrons will have energy to move to conduction band. At room temperature, all electrons at ED have sufficient energy to jump to conduction band. Electrons in conduction band are carriers, hence N naught increases but no increase in holes or P naught because no holes are created in the valence band. These are the comparison between the intrinsic semiconductor and the N-type semiconductor. In the intrinsic semiconductor, electrons that goes into the conduction band is from the material itself. Thus, electron that jump from EV to EC will create a hole in EV. Thus, the number of electrons in N naught is equal to the number of holes, P naught. For the N-type semiconductor, electrons that go into the conduction band are from the donor level created by the donor dopant. The electrons from the donor level creates free electron but do not create extra holes in the valence band. Thus, in N-type semiconductor, number of electrons are larger than the number of holes. Next, we are going to discuss on the P-type semiconductor. When an atom with 3 electrons in the outer shell from group 3, such as boron, substitutes the silicon atom, the silicon atoms nearby the boron atom would like to have 8 electrons, but they are collectively 1 electron short. So, an electron from the nearby silicon atom occupies the empty state. This creates an empty state at the neighboring silicon atom, and boron will be negatively charged because it receives or accepts an electron, and that's why it is called a acceptor atom. One boron atom will create one empty state, which is whole, in the silicon, without creating the number of electrons in the silicon. As for the band diagram, when a silicon is doped with acceptor dopant, acceptor state Ea is created. When the electrons in the valence band has energy, even a very small energy will make the electron from the valence band to move to acceptor state Ea. This will create holes in the valence band. When the electrons go to Ea, this means that the acceptor atoms receive electrons, making it to become a negatively charged ion. In this process, no extra electrons are at the conduction band. Thus, in p-type semiconductor, holes are created, but no extra electrons are generated at the conduction band. Thus, the majority carrier in this type of semiconductor is hole in the valence band. Similar to the donor dopant, the acceptor atoms also are influenced by the temperature. At T equals to 0 Kelvin, the acceptor state Ea is empty. At room temperature, electrons in valence band have sufficient energy to fill up Ea, but these electrons are not carriers because only electrons at the conduction band are considered as carriers. However, the electrons filling up Ea leaves behind empty states in the valence band, thus creating holes. Thus, the p node increases. In this process, no increase in electron concentration. Thus, in p-type semiconductor, p node is larger than n node. Now let's compare all the three: intrinsic semiconductor, n-type semiconductor, and p-type semiconductor. For intrinsic semiconductor, the electrons in the conduction band are from the materials itself. So, for each electron that moves to conduction band, creates one hole at the valence band. Thus, n node equal to p node equal to Ni, in which Ni is intrinsic electron concentration. For n-type semiconductor, electrons in the conduction band are from the donor level formed by the donor dopant. Each of the electron that move to Ec from Ed creates extra electron, but no extra holes are created in the valence band. Thus, n node is larger than p node, which is not equal to Ni. The majority carrier in n-type semiconductor are electrons in the conduction band. Finally, for p-type semiconductor, holes in the valence band are created by the excitation of electron from the valence band to the acceptor level, Ea. In this case, no extra electron is created at the conduction band. Electrons at Ea is not counted as the carrier. Thus, n node is smaller than p node, also not similar to Ni. In p-type semiconductor, the majority carrier are holes in the valence band. For summary, extrinsic semiconductor is a semiconductor that has impurities intentionally added to it to increase number of carriers or carrier concentration to improve its conductivity. For n-type material, it is created by adding material from group 5 to group 4 semiconductor. In this process, atoms from group 5 material produce extra electron that can move freely in the semiconductor. We say that group 5 material donates electrons, thus they are called donor ions, and they are positively charged. Donor dopant creates donor level Ed near Ec. At room temperature, all electrons from Ed jump to Ec without creating holes at the valence band. Thus, n node is larger than p node. For a p-type material, it is created by adding material from group 3 to group 4 semiconductor. Atoms from group 3 material has only 3 electrons that can bond with semiconductor, thus create empty site or holes. For the semiconductor to form a stable configuration, atoms from group 3 accepts electron. Thus, they are called acceptor ion, which is negatively charged. Acceptor dopant creates acceptor level EA near EV. At room temperature, electrons from EV move to EA, creating holes. However, no electrons as carrier is created at EC. Thus, N node is smaller than P node.